All right, welcome back, everybody. It is November 7th, and we are patiently waiting for Addison's race here during fifth hour. Again, ask your teachers. Today, we will continue on in our chapter. We talked about all the exponential stuff. We get the exact opposite side of the coin today, which is pretty handy. So we're going to be looking at 3.2, and I'm going to pick a different color because I don't like that one. 3.2, can you guys see that color? Okay, in 3.2, our focus is on logarithmic, and this will be the last time you ever see me write this whole word, logarithmic functions and graphs. Okay, now henceforth, log, all that I will use. Logarithmic functions and graphs, we're just going to call them logs, and whether it's a log function or a log graph, that's okay. Now, for a moment, I'm going to do some, you know what, we don't need pink. Let's just go ahead and jump right in. We're going to define our logarithm real quick. So this is really going to, it probably won't be the last time, just so you know. But we're going to give ourselves a nice definition of what a logarithm is. And we're going to approach this in a couple of different ways. We could do just a pure mathy definition, but if we piggyback on the stuff that we saw yesterday, there's a natural way to kind of go about this. Now, for graphing them and stuff, it's kind of rough. But here is the basic idea. We're not going to go into graphing them today, not directly anyway. But if I wanted to sketch on this coordinate plane, and I'm going to make it so I can see both sides of it, or all four sides of it rather, all four parts. If I wanted to graph a to the x, could I sketch it roughly on here, even without numbers? A to the power of x. If a is greater than 1. No matter what, if I pick 0, a to the 0 is going to be what? So I'm not picking a true scale, but maybe that's 1. If I go over to 1, it's going to be a to the x, and it depends on how big a is, right? If it was 10 to the x, it'd be all the way up here. If it were 2 to the x, it'd be a little bit lower, but it's going to be just some general place. I'm going to put it here. And our third point would be -1 and 1/8, or 1 over a. Which, depending on what a is, it would change, but it would probably be somewhere like this. This is what we spent the last couple days graphing, these types of graphs. And it starts getting steeper and steeper. This is a graph of a function, and we don't know the value of a, which is the only reason I'm not putting a scale. Every graph that was growth, we've written like this. Now, that graph, is it a function, first and foremost? How can you determine quickly and easily that, yes, this thing is a function? Change your word. It's not the horizontal to test this. Does this thing pass the vertical line test? Yeah, and if you're not sure, you don't recall, I don't know why I did that. That's not what I needed. What? We're just going to check. Now we're going to check. And eventually my stuff's going to quit being dumb. All right. It passes a vertical line test. We all agree. I can't figure out how to make this move. Now, does it pass the horizontal line test? Now, this one, I'm just going to retry it. We'll see if it works. Here's a horizontal line. If I were to copy this and try to move it around a little bit, and I think it'll work now, I can see how many times does it touch? How about here? Is there ever a place where it touches more than once? Now, it might get really close down here, but because we don't zoomed in far enough, we just don't see it. But it does pass the horizontal line test. What is the significance of that? And I'm going to make 2 comments here. Ooh, it's 1 to 1, so that's what that means. I'm going to start making a comment here. Since f of x is 1 to 1, and I'm going to use the TIE Fighter, 1-1, then something is guaranteed to exist. So injective is another word, 1 to 1, injective, that's all the same. What must exist if a function, the inverse, its inverse exists? Now, as we deal with this, I'm kind of blending a little bit. We're just laying a little bit of forethought to think about when we start graphing these. If you want to graph a function and its inverse, how do we do that? There's a reflection over a particular line. You're going to be close. If you compose a function in its inverse, like f of g of x, and you want to say that they really are inverses, what does it have to equal?
0.
Not 0. What's the identity in functions? 1 is the identity for multiplying, because something times 1 is always that same number. So, not quite. So let's check real quick. I'm going to make a claim, and this is just, you guys are going to help me. We don't need to truly write this down. Here's f, and I'm going to say it's x squared. What is the opposite of an x squared, or what undoes x squared? So square root of x. These are allegedly inverses. Help me out, and we're going deep here. If I try to do f of g of x, how would I even do that? This becomes f of, what's g? Square root of x. And then that means in any place where f has that value x, I replace it with this. And it winds up with this. What happens when you square a square root? Okay, so we just get, and I know that you guys can see it, and somebody already said it, but I'm going to word it differently, and then I'm going to ask the question. We get the identity out of it. Like, that's what it means to be an inverse. If I add 5 and negative 5, I get the identity for addition. It's 0. If I compose f and g, and I get, what's the identity for functions? X. It means that they're inverses. Now, graphically, what we saw earlier in this year is that if we draw the line y equals x, and it's roughly here, it's pretty close to good, could I reflect this? Like, let's just try real quick, and you guys are going to help me get these points, and then we're not going to talk about graphs again today, but it's a nice way to kind of build a little bit of motivation. This point right here, it's always 0, 1, if it's a nice chill function that hasn't been moved a bunch. How did I get this point? That was 1 something. A? And this was? Good. Negative 1 and 1 over a. It's the same 3 points that we've been using every graph that we've done. Now, the only reason that I did these is because we're going to think about reflecting this point over. So I'm going to switch colors, and we'll do this. We'll do it in white. If I reflected this point over, do you agree it's about here? Now, something happens when we talk about a function and its inverse, and I'm doing this hand motion, not just for fun. It's something switches, right? What switches? Or all the x's and all the y's, right? The domain and the range switch places. If this is the graph 1 or point 1 comma a, and we switched them, what would this point be? A comma 1. If we switched this over, we wind up like right here. And instead of 0, 1, what would this point be? 1, 0. And all we're doing is switching the x and the y's, which is really convenient if we want to think about graphing them. This last one's the ugliest. It'd be about down here. What's that ordered pair? 1 over a and negative 1. And if you're struggling to see what happened, I'm literally just switching the x and y. That is what happens when we reflect. Now, this shape is similar but different. Can we see that it's still bent similar like the other one? Now, this white function that we just graphed, if you've never seen it before, and I think you guys have it, looks very similar to the exponentials, and there's a reason for that. This function that we just graphed is the inverse of our exponentials. This is it. And it turns out that this thing has a super nice way to write down. I'm for now just going to write that this is f inverse of x. Okay, we have graphed the inverse entirely without ever defining it. Now, you guys might be able to answer this question. What is the inverse of a log? Dang it. What is the inverse of an exponential? Every day it happens so many times. Okay, yeah, over and over and over. So what we have just done is we've graphed a log function without even necessarily having to understand what's going on with it. Now, that's cool. It's easy to graph. It gets a little different, but notice these same values, 1, 0, and negative 1 show up just like they did here. So if you can graph an exponential, realistically, you're going to be able to graph a log just as well. Now, when we get to that point, that'll be nice, but we need to be able to actually evaluate some of these. So within our logarithms, we have this little motivation to say, look, I know it exists. I can even graph and show you what it looks like, but we haven't really dealt with it. We're going to jump right in with what I would consider the most important definition of this section. So definition, or defining the logarithm. Now, these things were first worked out by a gentleman by the name of John Napier. And we're going to see some goofy stuff happen with it. Not goofy, but just language stuff that we might wonder, why is it called this? And we're going to see it. Okay. The logarithm has a very specific definition. There is no math that goes into this. It's going to look mathy because obviously we're in a math class, but we're not solving anything. This is just the definition. So here we go. We're going to lay a little bit of groundwork here. We're going to say that for, and we could say for all. Is there a symbol for that? For all? Or upside down capital A, but I would encourage you guys to use it. I'm going to write this for all, and it's here, upside down capital A, or a V with a dash. I'm cool with that. Okay, for all x greater than 0 and a values greater than 0 but not equal to 1, a greater than 0 and a not equal to 1. We get the following, or we have. And this is the most important thing that we're going to write down today. Okay, we have an expression that we can write as y equals log base a of x. Okay, now, when we say this, people get goofed up all the time. We're going to clean up a little bit of language stuff just to make sure that we all agree. When we write this, I said log, and what did we call this? The base. Did exponentials have a base? Like if I write this, that's an exponential. Does it have a base? What might we consider the base, do you think? You have a 50-50 chance. On this expression, what is the base, do you think? 2. The base holds stuff up typically, right? The base is here. The same thing exists. Now, in here, I'm just going to write this out so we can see how to say it. This is the base. You will hear me regularly refer to this, the thing that's in parentheses, and it doesn't always have to be, but I'll try my best to put it in there at least to begin with. This is what I'm going to refer to as the argument. Now, just like when we were doing our exponential stuff the other day, we had an argument in there as well. It happened to be the exponent, and that's fine. Now, when we look at this expression is literally read, I'm not going to write y equals because I think you guys know that. This right here is literally read log base a of x. That's it. This is y equals log base a of x. And here's where it's going to get mathy, and it already is kind of probably pretty mathy. We're going to go ahead and say this is true, and this is how we define it, if and only if. This isn't a theorem, but it's just saying, look, we can move back and forth between these two forms. What is the base of that logarithm that we just wrote? Everybody, because I think I heard Matilda quietly say it. A. So check it out. This expression right here in logs throws everybody for a loop. Turns out it is the exact same thing as saying a, and here's the weird part. This is not an exponent. If I were to write this big, it becomes clearer. If you were to write 2 to the x, does this feel normal for how we would write 2 to the x? No, can we all agree that's stupid? What's stupid about it? Yeah, that's obnoxiously large. Now, if we wanted to be like really formal about this, if I was writing big, we would say log base a of x. When we look at how silly it is when we like scale it up and say an exponential, this is definitely not the exponent, right? This is not the exponent. Even though it's written like where an exponent would go, they're different font sizes, which gets really specific. But if you agree that this looks dumb, then we'll avoid that. Okay. Turns out, if x isn't the exponent, there's only one other option for it. We have to cross over. And it's weird that we do this, but a to the, what do we say this was equal to? This whole expression equals what value? A to the power of y equals x. Now, there's no real good way to say, like, if somebody says, why is this the case? Because it's the definition. And I know that that's not very satisfying, but that's all it is. There's no logic that goes into this other than this is how we all agreed. I wasn't part of the choice. It's how everybody in history doing math agreed to write it. Realistically, it's how John Napier, the guy who discovered it, decided to write it, and he gets to pick. Okay. Now, as we look at this, it means that we now have a way to calculate out logs. If logs are hard to think about, which most of the time they are, it's okay, because exponentials are way easier to think about. We're going to do a couple problems and then we'll take a quick brain break because I can tell that this might not be the most exciting. So here we go. For our first example, I just want us to evaluate each of the following. So evaluate. Now we could treat it like a function if we wanted to, and we will of course treat it like a function. I'm going to keep this definition up there. When you're doing the homework, if we get to homework, this would be the one thing I would suggest you write on top of your page. Like this definition. You need this. Okay, let's go ahead and knock some out. We're going to define or find some logs and actually just evaluate them. So here we go. I want us to find log base 2 of 32. All right, and to make sure we're all squared away, I'm going to let my calculator pick some random people here. And let's see here. There's only 11 of y'all. Number 7. What's the base of this? I don't know who 7 is. 2. 2. Do we all agree with that? Okay. Number 2. Weird. What is the argument of this logarithm? 32. Does everybody agree the argument is 32? Now, anybody know what this is right off the top of your head? Okay, we're going to pretend like everybody just said no. Most of you don't, and that's okay. You're going to, and you're going to be able to do these in your head for at least nice numbers. Can we agree that we don't know what it is, but it must be equal to something? I have a base that's an a value that's greater than 0 and not 1, and an argument that's greater than 0. Yeah, I can do this. If we don't know what something is equal to, can we just say it equals something that I don't know yet? And like that'd be a weird thing to write there. Can you guys see this color? That's a little dark. Can you see this color? Is that the same color? Weird. Everybody see that? If I don't know what it is, can I just say, well, I don't know, it's something. We'll just say it's y right now. And it feels like a weird thing to do, but here's the benefit. As soon as we can agree that it equals something, we just don't know it, we can leave our log notation behind, and we'll just treat it like an exponential. What was my base again? So by the definition of this is the definition, and I'm going to refer to that over and over. You don't have to physically write this unless you want to, but I'm going to ask you all throughout this chapter, what's the definition of a log? This is what I'm talking about. This is exactly the definition that I'm referring to over and over. Okay, we're going to use the definition of a log to make sense of this. My base is 2, and this is the only weird part. What's the power? Good. Not 32, because that would look silly. We're not going to use it. 2 to the power of y equals 32. As soon as we get this, does it really feel like we're in a new section? No. All of a sudden, we just kick back to the stuff that we did in 3.1. I can either make these both base 2 or both base 32. Which one would you prefer? 2, for sure. I agree with you. So 2 to the y is equal to, how do I write 32 as a power of 2? 2 to the power of 5. And as soon as I have this, notice my bases match. And all of a sudden, I'm having deja vu. I couldn't tell if I had used that language before, but I guarantee yesterday when we were doing these problems, we kept saying, do the bases match? So we did talk about the bases there. If you don't recall, that's okay, but we did. What's y? We all agree that y equals 5, and therefore, we could conclude, and you don't have to do this every single time, but it's good practice to start with. We just found that log base 2 of 32 is equal to what? 5. Now, immediately, some of you are going to be much more comfortable with these than others. The equals y trick will always work. It allows you to set it up and make stuff work nicely. Where I'm hoping will be pretty quickly, and we'll look at one more. We'll do it the whole way, but I want to show you guys where I want you to wind up. On B, let's do log base 3 of 81. Now, I'm going to have you guys attempt it the same way here right now, I guess. I want you guys to solve this log for me, and then I'm going to show you what I want it to look like once we're comfortable with these. I'll give you like 30 to 40 seconds if we need it. Addison, if you're watching this, pause it now and try this and see if you get the right answer in 3, 2, 1. So check it out. You guys get 4. And here's where I wanted to get to. Did you all do the equals y thing? Cool, that's fair. What's the base? 3. When I see expressions like this, and when you see expressions like this, my goal is eventually we don't have to do this every single time to solve it. Now, if you have to, that's okay. You'll be fine. But if we can identify the 3 here's the question in my mind. 3 to what power gives me 81? That's like how I think these things through. That is word for word how I would think this out. I'm going to write that because, again, you'll hear me say that. Yes, ma'am. Okay, I also have a question for you. What is log base 3 of 81? Fair. Fair. 4 is what it winds up being, but we'll get there. Okay, this thing, 3, and you guys, up to you, but this is how I'm going to word it every time. 3 to what power is 81? That is all this is asking. Now, it's just the opposite way of thinking about a logarithm, and I know it might not feel super opposite right now, but if you can answer this question without doing the equals y stuff, you're golden. Now, if you want the equals y, or if you got something different, I noticed one person using x. Realistically, you can use whatever you want. Much more common that we're going to use y because we're going to write functions y equals instead, but any unknown here. Your next line is probably 3 to the y equals 81. And then nobody elected to write 3 as a number of base 81. Everybody went the other way. Nobody wrote 81 to the 1/4, right? Okay. So 3 to the y equals 3 to the 4, and just like that, we get 4 out of it. And it's the exact same answer that we would get if we just posed this. Now, you do not have to know a ton of different powers. Like, I don't know 3 to the 5 off the top of my head. Not a clue. I bet it's 243 now that I think about it. But I didn't really know it. I just multiplied by 3 one more time. If you can do the first few, you'll probably find the right way through it. Now, we're humans, I believe. Do we need to do another one? Blah, blah. Rewind. Do we need to do another one like these, or are we cool to move on? All right. Now, we are all humans, pretty sure. Yeah. How many fingers do you have?
4. 8.
Okay. So, thumbs are fingers, just for the record. Thumbs count. You have 5 on one hand, and you have 5 on the other. So, yep, 5 from one hand, 4 when she didn't count the thumbs. And she said, no, I have 2 hands. There's 8. And I get it, but we'll just say humans have 10 fingers. Okay, do we all agree most humans have 10 fingers? Not all, but most do. Now, when we count, we essentially, if you can count 1 to 10, I might argue that you can count to any number that you want. If you know 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, you're golden. Or I would even say if you know 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, if you know those digits, you have every number that you could ever write. Because when we count, we essentially just count in groups of 10, even if we're counting smallers. So for example, if we look at that, 21 is just 2 groups of 10 plus 1 more, right? Like we always do that. 20 is just 2 groups of 10. That's the word for it. We count in a system base 10 is what we count as. What do you think is a really common choice to use as a base, knowing that humans all naturally count with 10? Base 10 is really, really common. Now, it turns out it's not the best one that there is, but if you do anything with the metric system ever, we don't a ton here in this country, but base 10 makes so much sense. Now, in fact, log base 10 is so just a natural, I'm not going to use the word natural, such a common choice for human beings because of these 10 thingies that we have, that we're going to give ourselves a small little subsection. We're going to define the common log. Now, it is actually logarithm, but I'm going to quit writing that word every time. The common log. On your calculator, Matilda, I saw you playing with yours a moment ago. If you look on the left side next to 7, do you see a button that says log? Okay, it is so common that your calculator has a button for this. When we write this, the common log, I'm going to say it and then we'll just have a mathy definition. It is the log with base what, do you think? Good. Now, because it's so common, we have log base 10 of x. This is the common log. Because it is so commonly used, people get lazy. When you hit the log button on your calculator, does it show you base 10? No. In fact, it never will because, again, so common everywhere that if I just write log of x, what do you think I'm going to assume the base is? 10. If you see log written without a base, it is just base 10 every time. Now, some of these make more sense to use than others. It is above the ln button on your calculator. Does anybody recall what ln is? Okay, deal. So as we look at this, these are more calculator-friendly questions. I will even show you guys, as long as you can assure me that I don't really care if you can use the calculator, but it's nice to have a way to check answers. I'm going to show you how to calculate other logs on your calculator. Okay, so for this, we'll do a couple examples. We'll do one that's a calculator problem and one that's not, but I'm going to make you estimate the non-calculator problem also. So here we go. I'm not even going to name it. It's just common logs. I want us to work out log of, I don't know, 100. No calculator allowed for this one. Now, I know it's going quick, and even if this really and truly were the first time that you've seen logs, I wouldn't do this any different in algebra when I do it this year. What is the base of this log? 10. Now, when I'm asking for a value of this, we could do the whole equals y stuff. That's fine. What's the question that I'm going to ask you if you say, can you help me? Like, we scroll up and look. How would I word this? The other one, so log base 10, you don't even have to say it, you can just say log. It's understood that 10 is the base. But up above in your notes, you see me that I wrote something. If you wrote it down, 3 to something, I had something with a sentence. So that was a base 3, right? What's the question for this one? 10 to what power, or to the power of what number, is equal to 100? We all agree that it's 10 to the 2.
Yes.
If you can do that, congratulations, you're calculating out logs in your head. And it's easy. Okay, this is just 2. And if you want to write it, you can. I'm not going to show any work. We don't have to do the equals y. This is 10 to what power is 100. And that one's nice and easy. We can answer that in our heads. What if I did log of 1,000? 3, because 10 to the 3rd power gives me 1,000. Now, some of them can be harder to calculate. What if I wanted log of, I don't know, 231? Is that a nice power of 10? No, but pause for a second. We're going to see if we can't think out what this is approximately going to be. You will always be allowed to use your calculator. Back in the day, there were 2 ways that people would do this when we didn't have calculators everywhere. You either had a big book that had a bunch of values that you would have to find 231, and you would go to that page because somebody had already done all the work. Or there are these fancy things called slide rules, which if any of your parents are engineers or architects, you probably have one around your house. It's like a little ruler that has an inside piece, and you slide stuff around, and it calculates out logs. Like, it gets used to do this. Now, this one, let's estimate. This number is between 2 powers of 10, I think. Okay, so we're going to estimate it. This is not our main focus, but I just want to show you it's nice to have. 231 is between 10 to the power of 2 and 10 to the power of 3. Do we all agree with that?
Yes.
Is it closer to 10 squared or 10 cubed? It's closer to 10 squared. Now, that means that I know this is going to be between 2 and 3. I can already tell that. And my guess, and I'm roughly estimating here, 2.2-ish is my guess, because I'm closer to 2 than I am 3. I have no idea what this is in reality, but when you type log in your calculator and type in 231 for your argument, it'll tell you what number. 2 point something. Ooh, I was not. Let's go, unless specified, 10 thousandths. That's 4. 3666, Dios míos. Like this? 3636. Okay, thank you. Okay, now, is that between 2 and 3? Yeah, now, I would really just ask my calculator, but it is nice to have the ability to kind of check these. All right. Doable? What's log of 10? Not on your calculator, in your head. Log of 10. 1, because 10 to the 1 equals 10, right? Now, I'm not going to give you guys homework over the weekend, just so you know. We'll do a quick brain break, but I want to get a couple more things written first. Okay. All right. Last thing that we're going to leave off with, and then we will come back in on Monday firing off these properties that we're about to list. Just to show you, I can't show you here. We just did a lesson in calculus yesterday where these properties get used like constantly. Logs, they do a lot of really valuable things all over mathematics. just so you know, like it's super valuable. But what we're using them for is calculus. In calculus right now is turning a problem that would take 15 or 20 minutes into a 2-minute problem. Like there is super value within these. I promise there's use for them outside of just playing with, the pure math. Okay, so as we do it, we get some really common properties that you guys are going to help me work out. What's our bullet point that we're working under? Logarithm? Yeah, I'm fine with that. Properties. Okay, so these properties, they are going to work no matter what our base is. Now, when you see this in a book, we could approach it as log base some number, but we could pick whatever number we want. Do you want me to use log base A or just log? Log is less writing, and that, just to remind me, if I just write log, it's log base what? 10. Okay, now there's a couple of them that we will do that with, but let's check out, we're going to mix and match whether we do it. The first property, and these are in no particular order. If I wanted, and it's going to feel like I just disregarded, I promise I didn't, but there's a reason I'm changing it, sorry. Log base A, not of x, of 1. Now, right here's a good natural place to just ask a question. I didn't put parentheses this time. Is that okay? Yeah, if I put parentheses, it's really specific about what the argument is. But if I don't put them, what is the argument? 1. Now, if we wanted 1 plus another thing, I would have to use parentheses because otherwise I wouldn't ever get the whole picture. But check it out. Let's see if we can't work this one out. No matter what A is, A to what power to get 1? 0. Boom. Log base A of 1, no matter what this is always equal to 0. Now I'm going to add these little pieces. Remember, I suppose, this symbol means because A to the power of 0 is equal to 1. Okay, always the case. Doesn't matter what the base is, which makes me think, man, there's probably a really easy point when we get to graphing these that we can use. Okay, on our second one, what if I wanted log base A of A? One. Why? Good. It's exactly because A to the 1 is A. Like, that's it. Okay, this one is going to look wonky, but I think we'll be able to work it out. I want you to talk quietly with your neighbors, and I wish I had some music going, but I want to hear a good argument. What's log base A of A to the x? Don't just shout it out. Talk with your neighbor. Once you have that and you think you're agreed with your neighbor, then I'm going to write one more property, and this is the last thing in the notes today. We're going to say log y.
Yeah.
Good. If you look at 3,
You know what I said? Well,
yeah, okay, for this one, log base A of A to the x. If you struggle with this one, it's weird, but it's so much easier than you might think. When I ask this question, I'm always going to think A to what power gives me A to the x? An x. And it seems silly to write, but we're going to say because A to the x is equal to A to the x. And it seems silly and obvious when you write it here, but it does work. Okay, our last one. This is a property that we saw with exponentials the other day. This is kind of like that injective or one-to-one property that we saw with logs. What do you think is true if I make the claim that log base A of x is equal to log base A of y? So they do have the same base. That's, I agree. Any other conclusion that we can come to? X must be equal to y. There's no other option because for it's 1-to-1. There's only one choice. And if we get the same number, it must have been the exact same argument. Okay. These properties get used pretty regularly. We're going to use them when we're graphing stuff. I'm okay to stop here. Cool. All right. Volleyball, pep club, anybody?